on building your own flash lamps. I'm not going to describe today how you build the type of flash lamps that you'd be able to buy from commercial sources, either buy them on eBay or from the companies that manufacture them. These higher pressure xenon type flash lamps that you'll either see in DJ type of strobe lights are very inexpensive. This is a $15 lamp. It's made with quartz. It's filled with xenon. And for very low pressure, very low energies, it's a very efficient way of making light and not expensive. It's not worth trying to figure out how to do that yourself. This is a scientific grade lamp. This was built for one of my other lasers. And this has been produced out of very high grade quartz. It requires pretty good glass blowing skills because you have to be able to handle very high temperature glass blowing when you're dealing with quartz. It involves very high quality vacuum systems in order to be able to clean out the tube sufficiently to be able to seal it, and then a xenon, very expensive gas, handling system to fill them. Even with all that kind of capability, this lamp is about $200, and so it's a pretty good deal if you're going to end up needing this kind of a lamp. But the kind of lamp that I'm going to show you how to make today is not one of these standard lamps. It's going to be what's considered to be a low pressure or ablating wall lamp. And that type of lamp is often thought of as a poor man's version of a xenon flash lamp. Like if you don't have enough money, you'll build your own lamp out of glass, a couple of electrodes, and a vacuum. You produce low pressures of a particular gas, in many cases air, and you generate flashes. And because it can be very inexpensive, it is an alternative if you don't want to spend the money for the xenon. But for the very highest performance work that I'm doing with very high peak powers, the wall ablating lamps, the low pressure regime, is actually more effective. It's better than xenon. And I'll explain why. Choose a glass that is going to transmit the type of wavelength that you want. And if you are, like I'm trying to do, deal with the very highest energies possible, then you're going to pick quartz, because quartz will transmit far shorter wavelengths than even Pyrex, which cuts off at around 300 nanometers. You can get down, even with the GE quartz, which is a very common quartz, down to about 190 nanometers, which is very useful because these things tend to run very hot, and that's where most of the advantage of these tubes comes in. Once the glass has been identified and the dimensions are identified, you'll want this glass to be fire polished on the ends, and you'll also want to have it annealed because they're going to be taking pretty powerful impacts and you don't want any stresses in the glass. The electrodes that you're going to use can be out of any kind of material you want. I built some out of simple aluminum, which is a very bad choice because it erodes very quickly. You can use steel, copper, brass. The very best material to build this out of is a material called copper-tungsten. That's what these are. Copper-tungsten is not an alloy, it's an amalgam. Copper and tungsten aren't soluble in each other, and so in order to form this material, what they do is they take powdered tungsten, they place it in a mold, heat it, sinter it, and then while it's still very hot, they introduce molten copper into the matrix, and they fill the voids so that there aren't any gaps between the tungsten particles with the pure copper. Once it cools, you have a very dense material that contains different percentages of copper and tungsten, different ratios, depending on the type of properties you want. A very typical ratio is 70-30, 70% tungsten, 30% copper. What's nice about this material, unlike steel or brass or copper, is it has a very low erosion rate under the influence of very high temperatures and very high currents. This material has a lot of the erosion resistance of tungsten, and at the same time has a lot of the thermal and electrical conductivity of copper. And what's convenient about this is that it's also extremely easy to machine. It's probably on the same order as brass. It doesn't gall and gum up like aluminum does. It's not as tough as stainless steel. It's copper is nasty to machine. If anybody's ever worked with it, it chips tools and it grabs. This stuff machines like brass, even though it is a very heavy material and it contains tungsten. I do it dry at medium speeds, use tungsten carbide bits. The tungsten particles don't seem to dull it, and you get a very nice finish when you're done machining it. And there's one more step I'll tell you about in just a little bit, but once you've made the electrode is then introduced into the tube, and the way that I do that, which is kind of an interesting technique, is they could be glued, but I've seen in a couple of papers where they're put on in what seems like a temporary fashion, but it turns out to be a very elegant way to do that. Once the electrode has been machined and cut to the proper dimensions, what you will then do is you'll take an O-ring. Silicone is a very good material because it has very high temperature tolerance. You will take this very sticky material and put in a little bit of isopropyl alcohol. For some reason, unlike water, the isopropyl alcohol makes this very slippery, and the material just will slide over the electrode. And within a minute or so it's dry, but it's an easy way to get it on without it grabbing onto the surface. I then take thin wall silicone tubing, again high temperature. Take a little razor blade, slice off an end, and then also make it slippery just like I did the O-ring. Take this and slip this over the end of your tube, all the way on there. While it's slippery, this is very easy to do. You see the tube extending from the end. Then just slip in your electrode and push your tube back over so that you can see the little bulge of the O-ring in there, and you're done. The way I fabricate this is in order to allow for a little bit of misalignment in the final flash lamp. You can see that this plays a little bit. And the advantage of that is that when you clamp this in some sort of a jig, if you're not perfectly aligned, you're not going to put stress on the tube. And during the shock waves that occur during the discharge, any kind of expansions due to either heat or just the shock itself can be taken up in this compliant material. I've yet to actually explode a low pressure flash lamp, and I'll describe that a little bit later, but were you to, or were you to drop it, or were you to eventually erode it, this is very easy to just remove, clean off this if you decide that you want to clean this off, and then just put it on a new tube. So very convenient. The fabrication of this material, as I said, it's very easy, but it's really easy if you use a lathe. And the way that I fabricate these is I'll take the raw material, which is expensive, about 15 centimeters of this diameter costs about $100. Feels as heavy as gold, but it's not quite as expensive. Once you put it in the lathe, what I'll do is I'll bore a large hole in the major part of the diameter here. Then I'll clean up the surface to bring it to the same diameter as the glass tube. And then through the larger diameter hole, which I drill in order to be able to tap the end of this for a hose bar, I'll then drill a second hole that goes partway into the thinner stem. That hole will then be punctured by a small lateral hole that gives access to the airflow into the tube. Then I'll turn down the upper half of the smaller part of this electrode, so that it's about 1 to 200 microns smaller than the diameter, the inner diameter of the glass tube. That's what gives it the play when you put it into the tube. The distal end of this is then brought down another couple hundred microns to maybe as much as a millimeter smaller in diameter. That decreases the thermal loading at the junction between the steel or the electrode and the glass. And then finally, before I part this off, I'll take a 45-degree chamfer this a little bit so that it brings off the end from a sharp edge, and then cut it off. I'll then take this in my hand, and I'll actually take some sandpaper, put it down on a surface, and just do some random rotations, spin it in my hand, random rotations, just soften the curve here to make it typical of a commercial electrode. This reduces the electrical field at the tip, reduces some of the sputtering of the material, and it also just makes it a little bit easier for you to insert this into the tube without cracking or damaging the glass, scratching the glass. This doesn't take very long to do, but requires one additional step. I don't have any cups out here, and I'm not going to do just for a visual, but basically what happens is this is copper-tungsten. And the problem with this is that the copper that's on the outside of this will still, it'll ablate under the high loading of the flash lamp. So what I do is, if you can see the color distinction here, I'll take the end of this when it's all finished, and I'll actually dip it in a cup of some nitric acid, concentrated nitric acid, for about 3 or 4 seconds. you'll see blue foam come off of the end of the electrode, and then it stops. I'll take it out, rinse it off with a little bit of distilled water, and put it back in the cup. After about 3 or 4 iterations, the foaming stops. Apparently I've gotten enough of the copper out of the copper-tungsten amalgam that the acid has difficulty getting in any deeper, and you really have just a surface of tungsten. The swishing is necessary because I think some salt forms on the surface with the nitric acid and protects a deeper erosion into the material. So if you swish it in the acid, it doesn't seem to clean it off, but you swish it in the water and it does clean it off, and you can do this iteration maybe 10 or 20 seconds in each vial, and you're done. Then this is ready to be turned into an electrode. The reason that you would do these low pressure flash lamps for high performance work is because the xenon is designed to operate at low to medium current levels and low to medium temperatures because it's a line emitter. What happens is when the capacitor discharges, sends a huge burst of electrons through, it stimulates the xenon to an excited state, which then spontaneously relaxes, producing the color bands of the xenon. Because xenon has the richest forest of emission lines within the visual spectrum, it produces a very white, very even, and very efficient output of white light. It's the most efficient gas there is. When you begin to drive the lamp harder and harder in order to produce enough energy for, say, a very high energy laser, what happens is the random thermal emissions that also are occurring become more and more dominant until eventually at the very highest energies you can't even see the xenon lines anymore. It doesn't matter what the gas is that you're using to produce the output. And at that point, the xenon becomes a disadvantage of the low pressure tubes. When they fill these xenon lamps to maybe 200 to 400 torr of xenon, they need to do so there's enough atoms in there to catch the electrons and to emit the light. But it also increases the impedance of the tube substantially. So what happens is when you put one of these tubes in this capacitor system, what you'll find is that the capacitor has a ringing frequency of about 100 kilohertz. It's got a discharge through, say, a spark gap or a dead short of about 5 microseconds. You take this particular scientific grade flash lamp, high pressure xenon, put it into this jig, and it will discharge in about 60 microseconds. It's the major impedance of this electrical system. If I do the same thing with this low pressure lamp that is actually narrower and longer than the lamp that I have here, this is an 11 millimeter ID by 27 centimeter electrode spacing. This is an 8 millimeter ID by 33 millimeter electrode spacing. It should be slower, but it discharges in 15 microseconds. The reason is that its pressure is about 10 to 15 torr. It's about 20 or 30 times lower pressure, very low impedance, and as a consequence, very fast discharge. What happens at low energies, and I'll show you in just a second, you'll see this. At low energies, the gases are acting just as they do in xenon, and they are doing a line emission. As you increase the energy and you go to higher and higher currents, the gas becomes hotter and hotter, and because there's so little of it, it becomes extremely hot. The hot gas impinges on the inner walls of the quartz. It ablates the surface. It disassociates the silica and the oxygen, which become the dominant gas within the tube, and is that material that's actually radiating out the light. So as the energy increases, the color bands decrease. It changes from its characteristic color, which for oxygen might be blue or argon blue. Nitrogen is sort of a pink. Helium is very pink. It'll go to white. You won't be able to see the differential in the color, and the output will continue to increase. What I think is happening here, though, is fascinating because the xenon lamps are filled with, say, 300 torr of xenon throughout the entire lamp, and when you run 3,000 or 4,000 joules through one of those lamps, if it doesn't explode, it sounds like it should, because the energy is so high. It's the energy of a rifle bullet. It sounds like a rifle bullet. There's a lot of pressure buildup because of a lot of gas in there. When you take one of these tubes and you put the same amount of energy through it and it discharges 3 or 4 times faster, it's much quieter. despite the fact that it's a more violent operation. Because of the fact that the pressure within the tube is so low, what I believe is happening, and this hasn't been really reported in the literature, even though there's a lot of description of ablating wall lamps, is that I believe spatially within the tube, it doesn't, the silica and the oxygen that are ablated from the wall do not distribute evenly within the tube and produce what's sort of a temporary silica-oxygen flash lamp. What I think is happening is the silica and the oxygen are forming a thin annular shell right underneath their source, which is the quartz wall. And the low pressure gas, whatever it is, nitrogen, helium, remains the dominant conductor throughout the system. And it is this gas, which is at enormous temperatures, maybe 30, 40,000 degrees K, that's producing the high velocity ions and the very extreme and very extreme ultraviolet photons, which are then absorbed by that outer layer and which is re-emitting them as a black body. The reason I think that's also true is because the pulse duration, if you increase the pressure with these tubes toward the pressure of a xenon tube, the pulse duration will continue to increase until it's similar to what the xenon tube is. If you leave the pressure low and you increase the energy, the pulse duration does not increase. It just gets brighter, but the pulse duration still stays very low. So I think the ultimate conductor doesn't change very much. It does increase very slightly from about 13 microseconds to about 15 microseconds. And I believe that's because the outer wall that has a thin annular plasma with the silicon and oxygen is actually constricting the low pressure regime a little bit, and that's what's producing the increased resistance. So with that kind of background, I'll show you basically what I do with the lamp once I've set it up. Once you put the electrodes together, you basically have now built this. And when you do that, you can put it in any kind of a jig you want, but you need a way to trigger it. The way that I trigger this is to take some very thin, this is 0.2 millimeter nichrome wire. I don't even know if you can see this on the camera, but it's hair thin. And it has a very nice property that when you twist, it holds a bend at very high temperature, and it's pretty easy to work with. And so what I do is I produce a sort of strap or a trigger array, just like the commercial people do, just like I did here, by taking the wire, wrapping it around the tube, actually tying a knot in one end of it so that I've got something to work with. It doesn't have to be particularly tight, it doesn't have to be a particularly neat job. All you got to do is you got to somehow get it to stay somewhat in that position. Then what I do is I'll cut off just a piece of this so I can show you the little technique. I don't spiral it around because that seems to cause it to sort of shrink in on itself if you don't keep the tension on it. But what I'll do is I'll form a little loop. I'll pass it underneath itself and sort of like a mattress. I'll form a little, I don't know what you would describe this, but it's a little bit of a retaining loop that keeps the free end in the same position by causing it to be trapped underneath the loop that you've just formed. So I'll wind it up like this, and with a little bit of skill you can make those line up pretty nicely. As you can see, I'm doing not a bad job. And as you weave this all the way to the end, you eventually will get to a point where the trigger wire needs to be a fair distance inside of the electrode so that it doesn't short out. It doesn't have to be very regular, because what it's effectively going to do, as you can see, if you can see it on here, is it's going to produce a low resistance component to this gap here, which you will set by using valves and the vacuum pump to be just slightly enough resistance to prevent the discharge of the capacitor. So what I've done here is I've set up this capacitor with a voltage divider so that we can see what the voltage is. This is a 1000 to 1 voltage divider. I've got a small grounding array of resistors here so that if we forget this for a while, it'll eventually dump the power. I've got this hooked up to a tank of pressurized gas at a relatively low pressure of about 4 or 5 psi, inputting freely to this needle valve. This is a fairly special component. It's a 0.02 millimeter square area needle valve, so very, very small area with a 20 turn adjustment. Very fine adjustments necessary because what you're doing is you're trying to just allow a very tiny leak into a free open vacuum system that would normally go down to about 1 torr. But when you add the leakage, you can bring the pressure up slowly to whatever pressure you need to just hold off the capacitor. So I'm going to show you with this thing not even cracked, so it's just about 1 millimeter, and show you what happens when the thing flashes. I'm going to turn on one of my other lasers and use it as a trigger. I'm just using its high voltage trigger spark to place a high voltage across the wires here, which capacitively couple to the low pressure gas in here and ultimately from there to the ground. You'll see the ground is at this end of the tube, the high potential is at this end of the tube. I'll go into that in just a second. Now what I'm going to do is I'm going to turn up the voltage here, and eventually you'll see, it should be on DC, at about 700 or 800 volts, this will begin to discharge. 300, and about 600 volts. And you'll see the flashes. If you look carefully at that, or I don't know if you can see this clearly, but it looks bluish. It's bluish because that's the line emission of the oxygen in the system. And so you're seeing the low pressure regime, which can be, these lamps can do a great job of producing and very inexpensively. As I continue to increase the pressure though, I'm going to be able to hold off a higher voltage and put a higher current through there. So what I'm going to do is I'm going to turn that off, and I'm going to short the capacitor. This is always exciting. Now, I can safely touch the valve. One of the safety things that I want to explain to you is that the low pressure gas in here is also present in here, and it's present in here, including the conductive valve. So you want the grounded end of this always to be to the side with the vacuum pump, because you don't want the high potential to be at this end where it could go either to ground this way or to ground this way and into your leg or the electrical system of the building. Always remember the high potential end needs to be the one that's isolated. This is high pressure air in there, and that's why I can afford to touch this and I can touch this even when this is charged. But this is always going to be low pressure, so that's why this is ground, this is high potential. I'm now going to open up the valve a little bit to a position where it's going to take a little more voltage to cause this to break down. Now we'll see what happens. It gets a little brighter. Okay, so I'm going to dial this up a little bit higher, and you'll start to see the white light that I was talking about. Now you can see it's a little brighter. It's tending to be a little whiter, and you can also hear a little bit more noise. We're only up at about 2,000 volts, so still we're only putting a few hundred joules in here. I'll turn it up one more time, and you'll start to hear the sound, and you'll see that the light becomes a much whiter color. Now finally I'm going to do a little bit more valve to see what that does to the hold-off voltage. I'm not really sure where this is going to be. Find out. That was up at about 2,000 volts, and I just opened the valve a little bit more, allowing a little more gas in, which means it's going to hold off a higher voltage before the trigger is able to fire. If you can hear the clicking of the trigger in the background, it's firing. It's just that there's too much resistance through the tube for it to discharge. As you can tell, it's now a lot brighter, and I think it looks a little whiter. This is so bright when it flashes, that you can actually see the trees behind the building through the windows. In addition, when you're as close as I am to this when it's firing, you can actually feel the heat on your face. A couple of the things though to keep in mind. These are ablating wall lamps, and one of the neat features is that even if you do use a lousy electrode material, the ablation process cleans the inner wall of the lamp. As you can see, there's no debris inside that lamp. A normal xenon lamp, after a few thousand pulses, will begin to look pretty funky right in front of the electrodes. The material that forms in here, whether it's copper, whether it is some tungsten, you can't clean that off with anything. Nitric acid, concentrated hydrogen peroxide, nothing takes it off, except ablation. I think the material actually gets embedded into the glass, and that's why you can't remove it. But because the ablation process cleans the tube, until the tube eventually is worn out, it's crystal clear all the time. The last warning I would give you is that if you look over on the other end of the bench, you'll see some power supplies. This is the right kind of power supply to use for this kind of a discharge because it has a positive and a grounded lead. You can ground one electrode is safe to touch, one electrode is safe to touch. This, which is a neon sign transformer, should never be used with these types of flash lamps. To save money and save weight, the high voltage leads on these things are not ground and high voltage. They flip 7,500 volts and 7,500 volts. It's a 15,000 volt transformer on each side of ground. If you put a rectifier on this, what you're going to end up with is a capacitor that's charged 7,500 up on one side and 7,500 down on the other side. Both electrodes will be lethal, as will your vacuum pump, along with your valve. This is not the power supply to use when you're doing this kind of work with these flash lamps. So that's pretty much it. I hope this was useful. This is the type of technology that I'm using right now for the much larger laser that I'll show you in a future video. This is the electrode material that I've cut for the flash lamps in this laser over here. Much longer, much beefier, and much larger in diameter. It's a pretty exciting laser. So thanks very much for watching. This was a lot of fun.